Okay, so hello everyone, and this is the third video for the week 3 lecture slides, and we're going to continue the review of the material. So earlier in the first two videos, we covered the introduction, then the tolerances, introduction tolerances, and the geometric dimensioning and tolerancing. Now we're coming to the third part, which is going to be about the fit. Now, just to give you a hint about the fit, and we talked about the tolerance, which we're going to have a clearance and variation in the dimension from the design value. Now, in the fit, we're going to have the interference between the two parts in most of the cases. So let's have a look first about the definition of the tolerance. It refers to the clearance that are going to be permissible between two mating parts in a mechanical device. That must be as simple, easy, and that must often move relative to each other during the normal operation of the device. So it can be either relative looseness, which we're going to have clearance fit, or we can have the tightness, which is going to have the interference fit. So I told you about some examples earlier, like for example, we're going to have the bearing that have the two sleeves, and the upper one is going to be sitting in a hole in the body of the machine, while the inner one is going to accommodate the shaft. So the fit between the shaft and the bearing inner sieve is going to be tightness, where the shaft needs to be sit there firmly, while the outer sieve is going to be actually sitting in the hole with a relative looseness, so I can take it out whenever I want. So specifying the degree of the clearance or the interference is going to be one of the tasks of the designer. The three types of the clearance, once again, is the clearance fit, the interference fit, and the transition fit. And you can tell that actually from the diagram we have here. So you can see that this is a shaft is going to have the maximum and minimum diameter as shown here, and this will be the value for the tolerance. Now we're going to have the hole. So between these two shaft and the hole, we're going to have clearance fit, where the allowance is going to be positive 0.01 of the inch. Now if we're going to move to the other side, the shaft now is larger than the hole diameter. And in that case, we're going to have the interference fit, where the allowance is going to be negative 0.03 inches. So obviously what you can see here, this one can fit in and moving loosely, while for the other one is going to be forced to fit in and then is going to be stuck. So now you will understand that we are going to have the maximum clearance for the shaft, for the hole, and we have the maximum interference, minimum interference for the shaft in the case of the interference fit. In the case of the clearance fit, we are going to have a tolerance value only to be applied. So terms used in the metric tolerancing according to the ISO system are going to be: first, we are going to need the maximum size and the minimum size for the shaft, and we are going to have the maximum size and minimum size for the hole. So we can sketch a line here. You can see that this center line is going to be showed up. You can definitely see that this will be a clearance fit. So the value here is going to be fundamental deviation, and the value between the lower value and the deviation value is going to be called the international tolerance rate. So once again, between this line and the maximum size of the shaft is going to be the upper deviation. Between the minimum size of the shaft and this line is going to be the lower deviation. And of course, between the minimum and the maximum size is going to be the tolerance zone. So by that, you can simply find what are these values. So between the maximum size and this line is going to be fundamental deviation. Again, once again, we go back to the whole side. That will be the lower deviation between the minimum size of the hole and the deviation line. And the upper deviation is going to be between the maximum diameter of the hole and the deviation line. So this distance is going to be tolerance zone for the hole. This will be fundamental deviation zone for the hole and the tolerance. And that's international tolerance rate, which is going to be the IT number. So the clearance fit for clearance between two mating parts, like the RC and the LC, the running or the sliding clearance fit, the RC, that's what we call the running or the sliding clearance, is going to be the RC. It's going to have 90 classes, the RC1 to the RC9, ranging from the precision fit, which is going to be the RC1, to the loose fit, which is going to be the RC9. So usually, if I would like to have the precision fit, this will be more accurate design, and this will of course going to be more expensive. We can go to anything between the RC2 to the RC3 if I would like to have a perfect matching for the two mating faces. Now, the loosest of the class fit used when the shaft must be moved freely inside the hole or the bearing, and the positioning of the shaft is going to be not critical, and this fit will always going to be allow for the clearance between the shaft and the hole. The next slide will shows a table extracted from the ANSI standard, the B41 1967, for the clearance fit. So once again, you can see in this diagram that the maximum diameter of the hole is going to have less diameter than the, maximum diameter of the shaft is less than the diameter of the hole. So the minimum airspace now is going to be 0.002 inches, and this is the allowance, and it's always going to be positive in the clearance fit. So that's the table, and actually I have updated Excel sheet again to share it with you. It's going to be uploaded to the view today, and we're going to talk about it by tomorrow. So once again, these are the different classes, and you can see that we have a nominal size range given in inches, and we're going to have the classes of the range. So for example, if I'm going to talk about the class RC5, and the diameter of my my shaft is going to be, let's say, 1 inch. So I will go to the 1 inch, which is going to be between 0.71 and 1.19. So the 1 is located between those. And then I'm going to go to the RC5. So then for the hole, I'm going to have the standard limit is going to be, so the hole can be 1 inch and 1.1, sorry, this is in 1000 all the millimeters. But anyway, 1 inch and 1.012. And for the shaft is going to be 1 inch minus 1.6 minus 2.4. Once again, these are in thousands of the inches, as mentioned here. Limits are in the thousandths of the inch. So the value you're going to have here, you need to divide by 1000. I have the chart which is going to be in millimeters, and this will actually going to make your life much easier. Now, if I'm going to have a look about the designation for the standard RC clearance fits from the NSI standards, RC1 is going to be closed sliding fit, and this accurate location of the parts that must be assembled without any first-phase play. The RC2 sliding fit, where the parts will move and turn easily but not intended to run freely, and the parts may cease with the small temperature changes, especially in the large sizes. The RC3 is going to be precision running fit, again, precision parts operating at slow speeds and the light loads that must be run freely, and changes in the temperature may cause difficulties. The RC4 is going to be closed running fit, and this will be accurate location with the minimum play for use under the moderate loads and the speed, and a good choice for the accurate machinery. So you can see that every time I'm going to get with the an upper number, the clearance is going to be quite increasing. So in the case of the RC5 medium running fit, accurate machine parts for higher speed and or for the loads that are going to be for the higher than the loads at the RC4. The RC6 medium running fits are similar to the RC5 for the application in which larger clearance are going to be desired. The RC7 free running fit and reliable relative motion under the wide temperature variation in applications where the accuracy is not going to be critical. And the RC8, and this will going to be the loose running fit, permits for large clearance, allowing the use of the parts with the commercial as received tolerances. And the RC9 is going to be loose running fit, similar to the RC8 with the approximately 50% larger clearance. So now we need to talk about the locational clearance fit. The previous one was roller clearance fit, and this one is locational clearance fit, or the LC value. So this for the parts for which the control of the location is going to be desired, although that the parts were normally not going to be moved in relation to each other in operation. Now the LC is going to have 11 classes, LC1 to the LC4, which have the zero clearance, that means size to size, and the lower limits of the fit, regardless of the size or the class. Now the LC5 through the LC11, that's LC11, will provide some of the positive clearance for all sizes, increasing with the size of the parts and with the class. The tighter than the RC fit, but the shaft and the hole may be the same size. The locational clearance fits will allow for the shaft to be located more accurately than the RC fits, but may still be loose. With this fit, a shaft will move less freely inside the hole. Now we're coming to the third type, which is going to be the interference fit, where the inside member is going to be larger than the outside member, or the shaft diameter is going to be larger than the hole diameter. Now you'll say how to fit it. Well, the answer is going to be by force. So this is required to apply a force during the assembly, resulting in some of the deformation and the pressure on the mating surfaces. So you can see here that the shaft diameter is 1.2519 maximum and 1.2513 minimum, while the hole diameter is 1.25 and 12.506 maximum. So you can see that the minimum diameter of the shaft is going to be larger than the maximum diameter of the hole, and that cause we are going to have some interference between the two mating parts. So the smallest shaft is going to be 1.2513 inches, and the largest hole is 1.2506 inches, so that there will be an actual interference of the metal and mounting to at least 0.007 under the maximum material conditions, and the interference will be even more and if you're going to have the small diameters. So this interference is going to be the allowance, and the interference rate is always going to be negative. Now we have the force fit, which is designed to provide a controlled pressure between the mating parts throughout the range of the sizes for the given class. So once again, the force fit is going to have 5 classes, which is going to be the FN1 to the FN5, ranging from the lighter dry fit for the FN1 to the force fit, which is going to be the FN5. The next slide is going to show you the table extracted from the NSI standard B41 for 1967 for the force fit. We have the shrink fit, where one member is going to be heated to expand, which is going to be mainly the hole, while the other remain cool. And then the part is going to be then assembled with a little or no force. Also, there's another way that they can simply cool down the shaft and then they force it inside the hole, then start to expand in size. We have the locational interference fit, where used where the accuracy of the location is going to be the prime importance, such as the alignment of the dowel pins and the other devices, where the location relative to the another part is going to be a prime important. If you don't know what the dowels is, actually they are a pin that's going to be fit in one of the parts by doing the locational interference, and they're going to be a guidance for the other part, which is going to be sitting at the top, to sit in exactly in the position. Have 3 classes for the locational interference, the LN1 to the LN3, and that's the table we have for the FN classes. So again, if I get to have the same example, I have the FN3 and I get to have the diameters to be 1 inch. So I look at the 0.95 inches to 1.19, so it's going to be within that range here. And I will go to the FN3, so the standard limit is going to be for the hole is 0 and 0.8 positive, and for the shaft is going to be positive 1.6 and positive 2.1. Of course, these are in thousands of the inches, as we mentioned earlier. Okay, so you can see that the interference between them is always going to be positive. So there's no negative, no clearance between them. Now, the five classes or the force fits are defined in the NSI standard B41. The FN1 is going to be for the lighter dry fit, and the second one is going to be for the medium dry fit. The FN3 is going to be for the heavy dry fit, and the FN4 is going to be for the force fit. And finally, we're going to have the force fit, which is similar, the FN5, which is similar to the FN4 for the higher pressure, where in that case, we're going to be use the FN4 for the higher strength assemblies, where the higher resulting pressure are going to be required. So this is the location transition fit, or the LT value, used where the accuracy of the location is going to be important, like how centric is going to be, but where the small amount of the clearance or the small amount of the interference is going to be acceptable. Again, it has 6 classes, which is between the LT1 to the LT6. So in this example, you can see that the smallest shaft is 1.2503 will fit in the largest hole of 1.2506, when we're going to have the minimum diameter with the maximum diameter for the hole. While with the largest shaft diameter of 1.2509 will have to be forced into the smallest hole of the 1.25 inches with the interference of the metal of 0.009 inches. So the basic hole system, where the minimum hole is going to be taken as the basic size and the allowance is going to be assigned, and the tolerances are going to be applied on both sides of and away from this allowance. The minimum size of the hole given in this example is 1/2 inches, taken as the basic size, and the allowance of the 2/1000 of the inches is going to be decided on the subtracted from the basic hole size, making the maximum size shaft is going to be 0.498 inches. The tolerance of the 2/1000 of the inches and 3/1000 of the inches respectively are going to be applied to the hole and the shaft to obtain the maximum hole of the 0.502 inches and the minimum shaft of the 0.495 inches. Okay, so mainly when we're going to have these diameters, you can see that the maximum clearance is going to be the 1/2 inches, 0.5, minus the minimum diameter of 0.498. The maximum clearance is going to be between the minimum diameter, the maximum diameter of the hole and the maximum diameter of the shaft. So this is the NSI preferred hole basis fits according to the NSI B42 table. So you can see that for the hole is going to be the one at the top is going to have the capital letters. So till this line, we're going to have a clearance where the always diameter of the shaft is going to be less than the diameter of the hole. Now, when we're going to have the diameter of the hole is quite little bit similar to the diameter of the shaft, we're going to call it a transition. It's hardly interferent. Now, when we're going to have more interference, where the diameter of the shaft is going to be more than the diameter of the hole, then we're going to have the interference. Now, how we can know that? You can see that the whole basic size is going to be mainly from the clearance up to the interference at the H7. Now, if I get to have the shaft, which is going to be anything like the small letter F7 or the G6 or the H6, that means I'm on the clearance side. If I'm going to choose a clearance of the K9 or the K6 and the N6, that means I am on the transition fit. And if I'm going to have it more than that, like the P6 or the X6 or the U6, that means I have a full interference between both. So the basic shaft system, where the maximum shaft is going to be taken as the basic size, and an allowance is going to be assigned, and the tolerances are going to be applied on both sides of and away from this allowance. So in this example, like this previous one, we have the maximum size of the shaft is 1/2 inches taken as the basic size. The allowance is going to be 2/1000 of the inches cited and added to the basic size of the shaft, making the minimum hole as 0.502 inches. The tolerances of the 3 in 1000 of the inches and 1 in 1000 of the inches respectively are applied to the hole and the shaft to obtain the maximum hole of 5.505 inches and the minimum shaft of 0.499 inches. So that will be the ANSI preferred shaft basic fits, which is similar to the one that we've done earlier, but you can see that the terms is going to be quite different. So once again, we come to the clearance part where the H11, H9, H7, H6 for the shaft tolerance, while in the capital letters for the maximum for the hole tolerances, we're going to have the C capital 11, D9, F8, G7, and the S7. The interference, we're going to have the K7 for the hole and the H6 and the actually that now you can see that the hole is going to do the interference with the shaft and not the opposite. Okay, so now we're going to the specification of the tolerances. That's something we need to add to the drawings later, and let's see how we can read them. So we have the limit dimensioning where the high limits is going to be placed above the low limits. Always we're going to have the high limit to be placed over the low limit. So this is the maximum diameter of the shaft. This is the minimum diameter of the shaft. Here for the hole, this is the maximum diameter of the hole and the minimum diameter of the hole. Now if I get into using these symbols for that, I can write down that the hole is going to be equal to 40, for example, millimeters, and the tolerance grade is going to be the H8, where the H is going to be fundamental deviation, and the IT grade is going to be 8. On the other side, for the shaft, I will say that the basic diameter of the shaft is 40, and we are going to use the F fundamental deviation, the small letter of course, and the IT grade is going to be 7. Okay, so this will be the F7, which is the tolerance grade. If I'm going to go back to the previous page, you will know actually if these two holes and shaft are going to have what the type of the interference. By simply, first we're going to write it down that the fit is going to be 40, that's the basic diameter, with the H8 hole and the F7 shaft. So we have the plus minus method, which is going to be the neutral tolerances. So you can write down that the dimension is 1.87 inches plus 0 above and negative 2 in the 2 in thousands below. Or in metric, we can say that the diameter is 47.7 plus 0 minus 0.05. So that's the tolerance we can have for the dimensions. We can use the bilateral tolerances, where that's what we have actually in the unilateral. We have the plus minus, but here we can simply write down as plus minus as if it's going to be as one figure. So if the plus minus not gain, well, here they don't allow maximum more size, but they allow a lower size. That's what we have in these two examples. Here is allow for the more and less. It can be more by 0.8 and less by 0.8. So that's what we can use it in the bilateral tolerances or dimensioning. Now we have the cumulative tolerances or the tolerance stack up, as we can see in this example. So the total width is going to be 3 inches and the minimum is going to be 2.995. And this can be divided for each one of the sections can have 1 inch maximum and 0.995 inches minimum. It's same is going to be for the others. So if I'm going to add all the maximum, is going to be 3. If I'm going to add all the minimum, it's going to be 2.995. For example, this can be just 1 inch. So this number is going to be 2.900. And thus the accumulation is going to take me to the 3. The same thing actually is going to happen here for the baseline dimensioning. That's for the cumulative tolerances. So once again, we can have the same method to be done. Now, the tolerance-related machining processes, of course, the different machining processes is going to give you a different tolerances, as we mentioned earlier. The better tolerances you are going to have, the higher cost of the machine is going to be. So these are the range of the tolerances that we have from 2, and these are the tolerances that range of the size included. So you can see, for example, again, to have my example of the 1 inch, I'm going to come to this one. And the tolerance I would like to have is going to be something like, let's say 2 in 1000. So I'm going to come to this one. So let's check what are the operation I can get these tolerances with for the 1 inch diameter. So I will go down, I will get that the reaming can do that, the slotting, the planing, the turning, the boring, the shaping can do it, and also the milling can do it. The drilling, no, it's going to be even worse. So the small diameter is going to be the more precise machining processes. So the last part of the lecture today is going to be about dimensioning and tolerancing in the SolidWorks. So that in SolidWorks we learn that we can make engineering drawings. Now we're going to learn how to put we learn how to put dimensions, and now we need to know how to put the tolerancing as well. So dimension and tolerancing in the SolidWorks. In the CAD model, adding the dimension in the sketches only to fully define them. And engineering drawings, the adding all dimensions only and all the GT and T to show the design details. So we do the two-dimensional sketch. We make the three parts with 3D assemblies, and we create the 2D drawings again. When we're going to be in the practice session this week, I'm going to show you actually how to create engineering drawings from an assembly. So dimension on tolerances, to add the dimensions manually, sketch, smart dimension, tolerance, and precision. That's how to add the tolerancing. Geometric dimension and tolerances, to add the datum flag to the reference geometry, we have to do insert, annotation, datum feature sample to be selected. To add the geometric tolerance to any entity not dimensioned, insert, annotation, geometric tolerances to be added. So actually that's what you're going to have in the case when you try to make insert. You can find that the insert, you're going to have the surface finish symbols, you have the weld samples, the stack balloon, the balloon. Mainly we're going to talk about the surface finish symbol, and you can have the datum features and simple, the datum target, and the cosmetic geometric tolerances also is going to be required. So by today we finished all these topic, and next week we're going to talk about the theory and the application of the computer-aided design or the CAD modeling. Okay, so also again to have a tutorial for this week regarding the tolerances and fits, and we're going to give you some simple examples, and also I'll try to have a look about the quiz and give you some hints about that. Thank you for your attention and listening, and hope to see you in another session. Thank you very much.